Hello, my name is Thomas Mock, and today I'm going to talk to you about pH titrations. Okay, so the first thing we're going to talk about is the objective of this experiment. And the objective of the experiment first is to collect data about the titrations and then put it into a graph so we can see what they look like in a graph. And then the second is to find the Ka, pKa molecular mass of the unknown solution that we will be getting later in the experiment. First, you're going to need some items to actually do this lab. And that's going to be a 50 milliliter burette, 0.0991 molar solution of sodium hydroxide, a 0.100 molar solution of hydrochloric acid, 0.100 solution of acetic acid. And you're going to get your unknown solution later. And then you're going to need a large beaker, approximately 400 to 600 milliliters, a pH meter, which you're going to measure the pH with, and then a hot plate that can do magnetism to make the magnet spin inside your beaker. And so that's what the burette looks like, the beaker, and then the pH meter. But there are many different pH meters, so yours might not look exactly the same. And so for the experiment, first you need to set up the beaker and burette. So for the first part of the experiment, what you need to do is you need to put approximately halfway full of your beaker full with hydrochloric acid or acetic acid, depending on which one you want to start with. And then after that, you need to set the burette to where it's directly above the beaker and full of sodium hydroxide, all 50 milliliters. And then after that, you put the pH meter into the beaker to measure the initial pH of your acetic acid or hydrochloric acid. And when you get this number, you record it into your data table. And then after that, you slowly let the sodium hydroxide drop into the hydrochloric acid or acetic acid, depending on which one you did first. And then you measure every 0.2 pH on the pH meter. And so you'll measure the volume of how much has gone down out of the burette. And then you'll also measure the pH, which hopefully is only 0.2 more. But when you get to a certain point in the lab, you're not going to be able to measure 0.2 pH because it's going to jump really fast. So it's going to jump probably like 2 or 3 pH. And so here are some of the results right here for this. And so the results are from the strong acid, which is the HCl, and a strong base, which is your sodium hydroxide. And then there's the weak acid and weak base, which is your acetic acid. And, oh wait, that's supposed to be strong base, but yes, it's supposed to be sodium hydroxide. But the reason that we can tell instantly, even if we did not have the labels, that these were a strong base, a strong acid and a weak acid, is because we can see that at our initial starting value, right here, it's around a 2, which is where a strong acid should be. It should be around a 2 or lower. And then over here with our weak acid, it's around a 3 point something, which is a relatively strong weak acid, but still a weak acid. And that's one of the first things we can say. And right here is where we have our jump that I was talking about earlier, which is when you have put so much buffer, which is your sodium hydroxide, into the solution that the acid can't produce as many hydronium ions. So the production slows down, which means the pH is going to shoot up in the solution. And but soon it starts to level out to where it can start producing just a little bit more again. So this is how you get this nice curve that goes up right here, and then goes back around and flattens out again. And one of the things about this is you had to find the equivalence point, which is somewhere in between your where your jump is. And this equivalence point is very important because once you find this equivalence point, so this is for the unknown, we can also tell that this is a weak acid right here, even if they give it to us that it is a weak acid, but sometimes you won't be able to know if someone gives you an unknown acid. So, but we can tell because this line right here goes straight towards around a 4, which means that this is most likely a weak acid. And so for our unknown here, we're talking about the equivalence point. It's around like an 8.7 is around what our equivalence point is for this. So if we take half of that, which will be a 4.38 around there, and we'll put a vertical line here, then if we go straight across from where it intersects this line, straight across, we'll find our pKa. And that's how we find our pKa for each individual one of these graphs. And so for our calculations for this, since we find our pKa from the graphs, then we can do our experimental data up here, which I got from UCSB.com in their PDF about all of the weak acids and their Kas. And so if we take 10 to the negative whatever our pKa is, then we will find what our Ka will be for that certain acid. And then we take our theoretical Ka, and then we subtract, we take our experimental minus our theoretical, divided by our theoretical, times 100, 4%, and I ended up getting a 27.27% error, which is a little high, but when you compare it to the results that are back in the lab manual, for the Honors 160 lab manual for our pKa's and the molar mass, once we calculate molar mass, then it becomes pretty close. And then the equations for our unknown. For our unknown, we had to find out the molar mass of this weak acid, of this unknown weak acid. So first, what we had to do is we had to take our pKa, which we found from the graph, and then we were able to find the moles of NaOH using basic stoichiometry. And then we took those moles, and since it was a 1-to-1 ratio, we could just multiply it, and then we have our moles of unknown. And then